Yeah, now you can.
Okay.
Okay, and you can do this.
Ah, that's better.
Okay, guys, so what we have here, we have a really hard question. Why it's hard, okay? Because we're gonna use symmetry, okay? If you don't gonna use the symmetry, the problem is really hard. But if you understand what is the symmetry of the problem, it's gonna be super easy. So the idea of this question is to give you this kind of tools. So what we have some disk. Here the disk, okay? And it's got some radius R. And of course we in the class of physics 2, so this thing contains some charge, okay? Don't draw the charge, okay? I just want to give you, I'm gonna show you how to draw them right. And they tell you what is the charge density, which means how the charge is distributed around this disk, okay? So this one equal to, be careful, look what I'm writing. R, the coordinate R, which means the distance from the middle, divided by big R, okay, capital R, which positive and positive, cosinus theta over 2, squared, which means everything is positive, right? Multiplied by some constant. Got it? This is the charge distribution. This is the charge density, how the charge is distributed around this thing. And the question is, what is the electric field here at this point? 0, 0. Got it? Zoom people, you hear us? Everything is cool?
Yeah.
Yeah, everybody. Good. Okay. So, let's do it. Okay, so what we need to do right now is to understand what is the electric field here. We know that the electric field is what? Equal to sum of its part, right? So I know that I can divide this disk to small contribution, right? This one. What is this contribution is? dA equal to what? So I need to choose coordinates. And since I see this one at r and theta, it's more like a polar coordinates, right? So I can already know that the good decision gonna be this one, r d theta multiplied by dr. Which means this thing is the length of dr, and this thing is r d theta. And I can divide all of it. But I can see something really interesting happening here. You see this one? Let's understand what is the charge distribution here, okay? Because it's really special. First of all, what this term tell me? This term tell me that if I'm going far away, I have more charge. You see it? Which means if r is equal to 0, I have 0. But then plus, 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 plus. You see it? As far as I go in a linear fashion, the charge getting bigger and bigger and bigger. Okay? Also, I see that everything here is a positive, right? Which means that if I'm looking at here at the electric field, it's gonna make a pushing kind of field, right? If this is the plus, it's gonna make a pushing field. You see it? So the question is, where it's gonna end up pushing? That's the idea. What is this cosinus theta? Okay, this is, I think, the most problematic thing. And it's also cosinus theta squared. I'm sorry, it's not in a linear fashion, it's actually parabola fashion, right? It's becoming more and more and more and more charge at the edges. Okay, so let's understand this term. What does this term say? So we know how cosinus look like, right? How cosines look like? Cosines is start the strongest and then falling apart, right? That's how I remember it. So it starts at 1 and then is falling apart and start all over again at 2 pi. But I see something interesting. Here inside the argument, it doesn't say theta. What it said? Theta over 2. So it's actually stretching this thing. Okay, so what's gonna happen? So this is cosines theta, and actually we're talking here about cosinus theta over 2, right? So what's it gonna do? Here it is. So it's gonna do this thing, right? This is gonna happen. This is actually pi, but actually what is it? It's theta equal to 2 pi, right? So it's actually, let's do it 2 pi. That's what's gonna happen, right? And what I also see I see that it's actually squared, right? The camera see me?
Yeah.
There's somebody with the zoom camera. You're gonna be the boss of the zoom. Congratulations. What you need to do is to press to all the people. You just need to press here and here when I'm moving. Okay? Here and here. If I go to the right, if I go to the left.
Got it.
Perfect? And if you want to play with the zoom, you can also with the magnification button. So, what's your name?
Argo.
Arglo? Okay. So Arglo is going to be in charge of the zoom. Thanks him later. So also I see this square thing, right? So what does it mean? That everything is positive, right? So actually, if I want also to do it square, let's draw it here. Let's do it in other colors. So this thing is actually cosine square theta over 2 is actually looking something like this, like an S, right? That's what happened. And here it's 2 pi, right? So what I'm actually seeing, that the charge actually get disappear at pi, right? Exactly at pi. So which means here is the maximum, and here is the minimum. You see it on the cycle? So charge is, let's draw it again. So what's actually happened? You can draw another circle. I do it because I don't have a lot of space here. So what actually happened? So if this is my disk, this term actually said that when you go along theta, here you don't have charge, no charge. But as you go to this side, or go to this side, charge start to accumulate. More and more and more charge, and here is the maximum. You see it? It's 0 or 2 pi is the same. Do you understand?
Yep.
So this is a really evil, nasty charge distribution, okay? And I'm sorry doing that for you, but I think we can learn the most from it. And then nobody gonna surprise you in whatever question they're gonna come up, okay? So this is all the things that I can play with theta. Also put the cosines, also do something to the argument, and also do something to the overall term. Okay? So what actually we see here, let's try to understand what is the direction of the electric field. Okay? I delete this, I leave only this. So in general, if you want to find the electric field, what we're gonna do? We're gonna say that the electric field is actually a vector, right? E, and it have two contributions, right? Also, it looks like this. The whole equal to the sum of its part, agreed. But I can open this one, it's two vectors, right? It's dE at x, and also dE at y. So we actually need to solve it twice. And this is a problem. But if we understand the symmetry of the problem, we can make this stuff easy, right? How we can do it? Okay, so what we actually can do is, let's take another color, the blue one.
We wanted 0, 0, right?
What? Yes, we're looking for what's the electric field in the middle.
Okay.
So what we understand that we can see that this term, yes?
Just what you explained with the cosine, that on pi you have no charge. But it's not working good with the fact that with the radius you have more charge.
Exactly, but if cosine is equal to 0, it's gonna kill everybody. You agree with me?
Yeah.
Okay, so what Nomi said that, dude, agreed, the cosines play along, it's okay. But you have this term, which charge. And I said, yes, you're right, but this term is multiplied by the cosines. So even if you're really far apart at the edge, where this term is at maximum value, cosine is gonna kill it and say, dude, you're gonna be 0. Okay? Got it. Good. So let's continue. So what I wanted to see, that I see two interesting stuff here that's gonna reveal to me what is the direction of the electric field. First of all, I don't see any difference between this thing this part and this part. I don't see, it's like the same. It's like we have here some mirror, right? That's what I see. Agreed? You can see the cosines that here it's the same thing. You see it's the mirror here? So if I have here some charge, the same thing gonna be here. And if I here small charge, the same small charge gonna be here. You see it? That's what I see. I see symmetry in this direction. And other stuff that I see this term, also you know it doesn't matter. R doesn't care in which direction you go. It's gonna do the effect all the way, so it doesn't count. The really problem here is to understand this term. Okay, this nasty guy. So what I also see, I see that at this part, you see, at this is equal to pi over 2, and also this part, okay? I see that this part have a lot of charge, right? Compared to this part. Let's do it in green. This part have more charge than, let's take the red, than this part. You see the red? I don't know if the color is good. You see it? So what actually happened here? Y actually is like a magnified creature. If I look some here at some charge, I know that the same charge on the other side gonna be bigger because the cosines gonna make it bigger. You see it? Because the charge going to max here by theta, right? Maximum here. Remember, cosines at 0 become at the maximum value. So that's what actually happened. Okay, so I told you a lot of stuff, okay? Let's try to take the real value inside of that. So if I'm going to observe some charge, let's look at it. You can draw another cycle if you want. So if I want to observe this dq, okay? This one. So this one I'm going to apply some value, right? That's going to be the value. But I know that on the other side, we're going to have the same thing, right? We said that x uses a mirror, right? It's the same thing. So if this one push at that direction, this one going to push at the same magnitude, okay? So what's going to happen? This one going to sum up, right? But this one going to kill each other. I want to go that way. No, I want to go that way. So they're going to kill each other. But this one is sum up, right? So the general direction from that contribution is going to be that. But we know that we can also talk about the charge over here.
Yeah, it's smaller, no?
Exactly. Okay, Ben already told you what I wanted to say. But we know that this side is bigger than this side because of the cosines. Okay, you see the function cosine squared theta over 2. This thing gonna also push here and also push here. But it's gonna be smaller contribution. Agreed? So in which direction we expect to see the electric field?
That's
To the left.
To the left, and in the mathematician language, minus x. Okay?
X.
Minus x. That's what you expect to see. So now we're gonna solve the question after that, and what I want you to take is how I deal with these cosines, okay? That's the idea. I know it's a scary thing, but if you do it step by step, you understand what's going on, okay? So, let's solve it. So, first of all, what we can say about this term?
0.
It's gonna be 0. All the y gonna cancel each other. That's what I said here. And now instead of solving it for vectors, okay, I can solve it to simpler solution. I can say that it's only care about the dx. You see me on the camera? Only a dx. Then it's gonna be at the minus x direction. I promise you. Okay? You actually don't need to put this minus here. It's gonna come up probably at the equation. Okay? I'm moving to the other board. I'm moving to the other board. Yes, Nomi?
Can you explain again why is it longer on the x direction?
Why it's gonna happen at the x direction? Okay, so it's actually to explain this again. So if I'm gonna observe some random charge, let's say this is the q, I know it's gonna push me at that direction, at the E field, right? This one produced the electric field to all direction, right?
Right.
Agree? So I only care about the one in the origin. That's why they asked me. And it's gonna push me to this one. Okay. And I know that the x-axis, because of this theta creature, it's make the same thing on the other side. So if I want to account to that one, I know that there is always a charge at the other side with the same magnitude. They're gonna push me to this direction. And if I'm gonna sum them up, okay, vectorial summation, I know that all the direction of the y-axis gonna cancel each other, and all direction at the minus x gonna sum up. Got it, Nomi? Till now?
Yeah.
Okay, but there's other thing. We talked about that the y-axis is actually like magnify stuff. He said that everything that is around here, because of this creature, look what's happening. Everything. This is this line. Let's draw this. Let's draw the cosines in a bigger way. So the cosines is looking like this. This is the cosines. Actually, we said looking like a S, right? Because it was multiply square. And now I'm drawing all the quarters of the circle. This is gonna be 0. This is here. What is the value? Max. Right? And then I'm going along, I get to this point. This point is pi over 2, right? I'm going along and I get to here. This is 0, right? And here, 3 pi over 2, which is this place. And here it's again, repeat to what I was, right? Exactly.
Yes.
So what I see that this line actually, what is it? It's the y-axis. This one, nice. And another. This thing is the y-axis, right? Is this term? Is this line, right? What I see that everything at this side is smaller than this side. You see it?
Yeah.
Everything here must be smaller than this thing. So what it says that if you got a dq here, I promise you, according to that you have right next to it another dq. They have a little amount of charge. And it's try so hard to push you, but it's so weak, okay? So the magnification here, you know, they sum up, but it's still small compared to that one. Got me?
Yeah.
Perfect. We can move on? Good. Okay, so we said that all the contribution at the y direction always gonna cancel out because there is a friend. There's a friend on the other side, they're gonna cancel it, and it's gonna be for sure at the minus x because these guys in this half weaker than that one. Okay? So we're actually solving the question E. Let's do it on the other board. Move the camera, please.
Okay.
Perfect. Zoom person.
Not moving? Yeah, you just keep going. Yeah.
Okay,
Right,
so
totally.
E is equal to only contribution at x. All the contribution at y, which exist, will eventually cancel out. And I don't want you to calculate them. Because if you're going to calculate them, you're going to waste time. Okay? That's the idea of using the symmetry. And this symmetry going to repeat itself and you're going to be more familiar with that. Okay? When you're going to study to the exam. So we care only about that because this one going to be 0. So what's the value of dEx? dE equal to what?
Okay.
K, correct.
dq.
dq, correct.
dq.
Correct. And also divided by
d squared.
Distance.
d squared distance. Yeah, distance.
Magnitude.
Yeah, the distance from the charge, right? D squared. Okay? So I want to write this vector. So what's actually equal this vector equal to? It's equal to two different vectors. The first one is where I want to find my electric field. Right? Which is where? E00. That's what I'm looking for. minus, where is my charge? dq. This is the vector d. Okay? This is what it's equal to. This one, where we want to find the charge, the electric field at the origin, 0, 0. Where is dq? I can give it a random, not a random, but Polarian coordinate, r cosinus theta, without this, sinus theta. It's the opposite way? No, this way. Right? This is the polarian, that's what it said. So, what I want you to see here, that what is the magnitude of this creature is actually r, right? But what is the direction that this vector is pointing?
Negative x.
Not negative x. Be careful, this is the vector. It's actually, this coordinate is r hat, right? It's the radial one. But you got here a minus. You see it? So this actually, minus r hat, okay? This is super important. Did you got that one or should I repeat it?
But and what's the meaning of having minus r cover, like in the drawing, where is it gonna point down?
Which
like
this mean, okay, so what is radial? Radial, it's mean away. And what is minus radial? Through me, right? So that actually means that all the vectors gonna point at the radial, the minus r, right?
Right.
All the charges. Okay, did you get this part? So this is important.
Can you explain it again?
Okay, again. So this is the definition. Agreed? This is the definition. Nothing to argue about that. This is how you define the distance vector here. And it's equal to r the origin, sorry, not the origin. It's equal to where I'm looking for the electric field. Where do you want to find E? That's the place. Okay, this one. And in our case, it's the vector 0, 0, right? It's the origin. If it was other place, you should put it here. Okay? dq, where is the specific charge which producing the electric field? Where is it? So I said, let's do it general. And when I say general, I said this. The vector is actually, this is the dq that produce the charge, that produce the electric field by charge. I said, it's over here. Look, it's here. So what is this vector is actually equal to r, this distance r, and you got some contribution here and some contribution here, which is the radial one, right? It's radially pointing to this creature, right? And radial is equal to r cosine theta sinus theta, right? That's how you write it with two, x and y. Agreed?
So it's multiplied.
Yes, multiplied by them. Some contribution at x, some contribution at y. So this is a general term, and we see that this is the solution for that. And what I really want you to notice is where this minus coming from, because people forget about this minus. They forget that they need to, right? And it's always happening when people ask you on their region, they forget about this part, okay? They understand why I get the same solution, but I have a minus problem. Guys, if at the homework you think you got the right solution, but I have a minus problem, promise you, 90% is this thing, okay? You didn't define the distance vector. Okay, we succeed doing this, we succeed doing that. We still have to find dq, right? So what dq equal to?
It's the charge density.
Charge density, which is given.
Given.
Right? It's this ugly monster. R theta, right? Square multiplied by sigma, right? Multiplied by dA.
dA.
And dA is r d theta, right? dr. Agreed?
Yeah.
Agreed? Divided by this term, which is r squared, right? Multiplied by the direction, minus r, so minus r, right? This term. Yes? Perfect. What I see that this one cancels with this one, right? Because this is square, can get them out, and I still have to deal with that, so let's clean everything else. So what we have here actually, it's equal to minus, we have this minus is taking, I'm doing the integral right now. So it's integral dE, and this is equal to minus here, right? Minus here, integral k, this creature, sigma 0 over r squared, and actually I didn't start to, okay. So we have here r, cosines theta over 2 squared, multiply by, and now I can open this one, right? I have two contributions. I want here to write only dEx, right? So what I'm actually going to use, it's cosines theta and sinus theta. I know that if I'm going to sum up all the sinus also, they're going to cancel out. So I'm just going to use the cosines. So multiply by cosines theta. Okay, I do it in different color. So you understand this one is actually coming that I only want x. Only use x here. Got it? Perfect. And then here it's, I still have this d theta dr, okay? And all this, and I have two integrals actually, right? What is the boundary that I have in the integral?
0 to pi, 0 r.
The r is running from
Is up.
0 to r.
0 to r.
Great, we have started the origin. I sum all the charges until I get to the edge. So 0 to r, agreed. What is the angle that I'm running?
0 to 2 pi.
0 to 2 pi. I want to do all the circle, okay? So all this integral is end up to be pi over 4 with everything. So actually it's equal to minus k pi sigma 0 4 x hat. So this is the final solution. Okay?
When we are like in doing homework and stuff, define an integral like this, because like to integrate cos squared of theta over 2 times cos theta, it's kind of.
Okay. So I'm gonna tell you a real problem that I have in my research. Okay, in my research I had a really nasty integral that I need to deal with. So I open online integral calculator, and I just finish with that. And if I want to take a precautions, I'm gonna put in my notes for the exam this integral equal to that, and I'm gonna find out on the web how to solve this integral. The thing is that during your degree, you're gonna have a lot of hard integrals that you need to deal with them, and you need to learn how to deal with them, you know, each one individually. But at the end of the day, it's up to you, you know, it's your startup, it's your idea, it's your research, right? So each time you have a nasty integral, when it's on homework, it's expected to be hard integrals. Usually at the exam, we're going to give easy integrals, or we're going to say the solution to this integral is that, okay? But still, it can be expected from you to know the basic integrals to do. I promise you that I would not put this kind of integral at the exam, and if I would put an integral like this, I'm going to give you the solution, okay? Because I don't want you to waste time on the math. I want to waste time on the physics, because that's what I want to teach you at the end of the day. Okay? Good, guys?
I have another question around.
Yes.
The fact that you use the cosine only, it's only because it's the x direction.
Yes, exactly. I had a lot. Look. When I have this dq, back to here. When I have this dq, that's what I did actually, right? I had some contribution, and I said, okay, I want to calculate what is the electric field. And this one produced this one, this vector. And I said, don't look at this vector. Sum only this one, Ex. Don't waste your time. Don't sum Ey. Why don't sum Ey? Fun. Because when you're gonna go calculate this one, this charge, this charge, and this charge, what's gonna happen? this one gonna kill the one that you already summed before. You see what's gonna happen? So that's the
Yeah, I
reason.
got that, but it's just weird because you have EY in two directions, so you should add and cancel, right?
Exactly. I should, if I want to do it properly, I should add also E at the Y direction. But I told you, I understand what is the symmetry of the problem. And all the idea of this problem was not about Coulomb law. It was about specific function and how it affects Coulomb law. Okay? The idea was here to understand that cosines can actually make the problem really hard. This theta dependency. But you can get a void from it if you understand exactly how it's behaved. Okay? Otherwise, you should solve this integral twice. Cosines multiplied by cosines, which is easier than cosines multiplied by sines. Okay? That's the idea. Got it? Okay, so I saved you one integral. That was the idea here. Okay? Guys, do you have any questions from the homework that you want us to cover together?
Question 5 of the homework. It's
Okay.
the question of the infinite order.
Ah?
Questions 5 and 6.
Somebody want to write the question down so we can discuss it together?
Do you have it, Tadu?
No. Ron, some of us have like one more class now, so like.
Okay. So okay. So we can You can send me by email your questions. Okay. Okay, it's fine by you, and then we're gonna find time that I will cover it. And this question help you with the homework?
Huh? Yeah, but like the problem with the question, I think that most of us want to ask is a question about an infinite wire that we.
Infinite wire.
Yeah,
okay.
that we don't know. Our professor, she did a question
Okay,
about
so
this.
if you next time, if you have a question, send me the question before, and I can prepare a question that's gonna help you with the homework. If you have something that all of you feeling uncomfortable with, okay, for next time.
Okay.
Okay, and that is send me by email your question, and I will try to guide you through it. Also, you can send it to Michal, the lecturer, and we can help you. Okay. The question submission is to?
I think we still have like 8 days a week. It's fine.
8 days a week. Okay, so it's not on the rush, but send me as soon as you can. Okay. So thank you, guys. Enjoy your next class.
Thanks, Ron. Bye.
Yes, Nomi.
It was something I wrote on your YouTube channel, but you didn't see it yet. It was something, just to clarify, it's something pretty basic, but I wanted to show.
Okay, go ahead. Can you open the camera and show me? Ben, can you close the camera?
Huh?
We finish camera and microphone.
Okay, I have to press here.